In this section of the lecture, we will be talking about the properties of probability and ultimately these properties that extend from the three probability axioms that we looked at in the previous section of this lecture. So the first resultant property of probability axioms that we'll look at is that all probabilities are less than or equal to 1. Now, as you may recall, we kind of hinted towards this in the last lecture, but in this lecture we're going to spend a little bit more time discussing how that actually comes to be. And so the easiest way to look at this is to think that we have some sample space omega, and within that sample space we have some event or set that we'll call A. Now, in the case of this A, we also have a new area that we haven't talked about yet, which is that of A complement, or you'll see it written A prime. It can also be written as A with a superscript C to indicate that it is the complement of that event A. So basically anything in sample space omega that is not part of the event A is going to be part of this A prime. Now, typically I'll refer to it as A prime. Some of the other lectures that we'll use throughout this course will use the A complement or A superscript C notation. So it's important that you recognize both of those as meaning the same thing. Now, we can easily from this image note that the probability of A, which is again that probability of an event occurring inside that event, and the probability of A complement is equal to that of omega, which is 1. Remember, we have the normalization axiom that says that the probability of omega will be equal to 1. So with that, it's also interesting to note that the probability of A unioned with the probability of A complement is equal to omega. It's basically saying the same thing, but in a slightly different way, and you'll notice that this version actually just uses set notation to say that the elements within A unioned with the elements of A complement are equal to the sample space, or omega. And then finally, we can say, inferred from this as well, get some interesting information about the empty set, or the intersection of A and the complement of A. We can say that A intersected with A complement is equal to the empty set. Basically, because we've defined A complement as everything that is not A, that there is no area where A and A complement are the same. Now, logically following from all of these, since we know that the probability of A plus the probability of A complement is equal to 1, we can rewrite that equation to say that the probability of A is equal to 1 minus the probability of A complement. Now, as you may recall, we also have a non-negativity axiom that says that no probabilities can be negative, which means that this area, the probability of A complement, has to be greater than or equal to 0. From that, we can then infer that given that the probability of A is equal to 1 minus the probability of A complement, and that the probability of A complement has to be greater than or equal to 0, the probability of A must be less than or equal to 1. So again, this says in the most generalized case, and it follows for all cases, that the probability of A, or any probability, must be less than or equal to 1. Now, the next resultant property that we'll look at is that the probability of an empty set, or a set containing no elements, is equal to 0. And this intuitively makes sense, but again, we'll kind of work through a little bit of the math that goes into that. So we can say that the probability of omega plus the probability of the complement of omega, so everything outside the sample space that we're concerned with, right? We know that that is something that is not inside our sample space, has to be equal to 1. Well, since we're only concerned with probabilities within our sample space, we can thereby say that the probability of omega is equal to 1, right? We looked at that earlier. And also we can say that 1 plus the probability of omega complement, or in this case the empty set, is equal to 1. And so therefore from that, just subtracting out the 1s, we can say that the probability of the empty set is equal to 0. Now the next property that we'll look at is that of the extended disjoint probability. As you may recall, we looked at in the previous section of this lecture a axiom, which was that the probability of A unioned with B is equal to the probability of A plus the probability of B, so long as there is no overlap between A and B. And we kind of showed that implicitly through a graphical manner, and we're going to extend this now to more than just two events. So in this case, we'll look at the probability of A unioned with B unioned with C. So if we draw this out graphically, we have some event A and some other disjoint event B, and then a third disjoint event C. And all three of these events, again, for it to be a disjoint probability, cannot share any overlap. So from this, we can say that the probability of A unioned with B unioned with C is equal to the probability of A unioned with B, that unioned with C. Again, just extending set notation, this goes back to basic sets. From that, we can then get the probability of A unioned with B plus the probability of C. And from there, again, just using that initial axiom, we can split that to say that that is the probability of A plus the probability of B plus the probability of C. So we're just using that same axiom that we developed in the previous section of this lecture and extending it to multiple disjoint probabilities, or more than two events. And if we generalize this, we can actually go so far as to write a pretty ugly to look at but very powerful equation, which is that the probability of A sub 1 unioned with all of the individual A sub i's up through A sub k is equal to the sum from I equals 1 to k of the probability of A sub I. Again, basically saying the same thing, that I can take the probability of multiple discrete disjoint events and sum the probabilities of each of those individual events together to arrive at the probability of the union of all of those events. The next property we'll look at is what I like to call contained probabilities. And this is basically saying that if we have a event A that is some part of an event B, or more accurately, a set A that is some part of a set B, then the probability of A must be less than or equal to the probability of B. So to look at this graphically, again, we have some event A, and then we have some event larger than that that is B. And B is all of A plus B itself. And so, again, from this, we're going to try and show that if A is a subset of B, then the probability of A must be less than or equal to that of B. So another way to look at this is to say that B is ultimately A plus the union of B intersected with A complement. So we're going to say it's all of A, this area right here, plus or unioned with the area that is B intersected with A complement. So A complement is everything outside of A. That intersection with B is going to be all of this space out here. This area that is not A, but part of B. Since probabilities cannot be negative, that means that this probability of B intersected with A complement has to be greater than or equal to 0. And in that case, that means that the probability of A must then be less than or equal to the probability of B. Again, pretty intuitive. When you look at it graphically, this is more the mathematics derivation behind it. The next property we'll look at is that of non-disjoint sets. So this is two sets that do have overlap. So this would be if we have an event A and then an overlapping event B. In this case, there is some area A that is on its own. There's an area of B that's on its own, and then there's an area where A and B overlap. And the generalized form of this is actually pretty simple to look at. We can say that we have the probability of our area A, so we'll call that probability of A. We have the probability of our area B. And with that, we have this area in the middle that is represented twice. So we need to remove that from our overall equation once so that everything is included only once. And the easiest way to do that is to simply subtract the probability of A intersected with B. And you'll see that over here, that the probability of A unioned with B is just the probability of A plus the probability of B minus the probability of A intersected with B. Now, if we want to take this a step further, we can really break this out into three elements. There's what we'll call a little a, that is the probability of A intersected with the complement of B. There's the B, which is the probability of A complement intersected with B. And then this probability little c, which is the probability of A intersected with B. And so if we look at that in a slightly different manner, what we're really saying is that this A intersected with the complement of B is all of the area that is part of A and is not part of B. So that's going to be this area over here. And just so we have a little bit of a legend, the other area that we can look at is the area B, or little b. And so that is the area that is part of B, but is not part of A. And so again, that's going to be this section right over here. And then the last area that we can look at is little c, and that is the probability where A intersects with B. And so that is the area that is shared between both probabilities, or both event spaces. Now, the next step in this is to say that the probability of A intersected with B is really equal to the sum of these three regions, of the probability of A intersected with B complement, the probability of A complement intersected with B, and then the probability of A intersected with B. And so from this, it follows ultimately another example, which is that because each of these probabilities here, the A, B, and C, must be greater than or equal to 0 by the law of non-negativity, we can derive a new equation, which is that the probability of A unioned with B, this total area, must be less than or equal to the probability of A plus the probability of B. Now, the next example that we'll look at is that of non-disjoint sets, and we're going to extend it to more than two elements, or more than two event areas. And so in this case, it's actually fairly simple to look at. If we have an A a B, and then some third area C, we can write this probability, or this set space, as the area A, so everything that is A, including that which is part of B and C. We then look at the area that is not part of A, but is part of B. And then finally, we look at that part which is not part of A, not part of B, but is part of C. So this is, again, graphically pretty easy to understand. And we're going to really leave this one at graphics just for the simplicity of it. But the important thing to note here is that the probability of an event A unioned with that of B, unioned with that of C, is just equal to the probability of A plus the probability of A complement intersected with B, and the probability of A complement intersected with B complement intersected with C. Again, we're basically just eliminating these areas in the middle that are overlapped from being counted more than once.